Alright, Math 123P, looking at supplement C5. This is a help video associated while I make the key. I figured I might as well make a video, and if you would like to watch for any particular problem that's been giving you trouble, skip to that point in the video, or just watch the whole thing and learn some new stuff. Here we go. We'll just kind of jump right in here. We're trying to find the y-intercept of this thing. Was showing work in writing your answer as an ordered pair. We actually talked about this in class today if you are 1028, 2025, Math 123P. But I'm going to go over what we talked about real quick. So first of all, we're talking about an exponential equation, or exponential function, I should say. This is one of the general ways to write such an exponential function, where a is kind of your starting value, b is your multiplier. We'll talk about what that means. And x is the kind of the counter. Typically, we can call that number of periods if you're looking at it in an interest or sort of way. But this kind of just is a count. We're counting something. And then this, of course, will be our output value. If we're looking at interest, this would be the total amount of money for a one-time deposit after a certain amount of interest is applied. So a couple things to think through here. First of all, if we're going to do interest, and we might as well because that's all section D, typically we give interest as an APR. That's an annual percentage rate. And I'll even type that. Annual percent rate. And an APR, let's say 5%, and just to be tricky, we'll do 5.3%. Would be every year you get 5.3% of what you deposited added back to your account as interest. So as 5.3% as a decimal, percent, by the way, means out of 100, like this. So 5.3% is 0.053, like that. That's 5.3 divided by 100. And let's say we deposited $100, you know, and we have this 5.3% APR, and we get a interest compounded yearly. That means our interest is applied yearly. So we take the total amount of interest and we put it back into the account, and then for the next time we'll get interest including the amount we got the first interest compound period. So let's look at this. The output, or number of dollars in this case, would be the starting value, $100, multiplied by the multiplier. And the multiplier, just to make this clear, is we're going to multiply 100 times something, and then we're going to do it repeatedly. That's what that exponent means. So if we put 2 as the multiplier to the x, this would repeatedly take 100 and multiply it times 2. Over and over again, 100 times 2 times 2 times 2 times 2. And that would double every time, right? But we don't want to double. We want to go up by 5.3%. And if you notice, if I were to multiply this by 1/2, or 50%, it would get smaller. So for numbers less than 1 but higher than 0, things are going to get smaller. But for numbers greater than 1, things are going to get bigger. So looking at that from a percent perspective, 1 is 100%. So if we multiply by 100% or 1, it's going to stay the same. It never changes. It's just always 100. Cool, right? We want to go more than 100% though. We want to go 100% plus this much more, 5.3%. So 100% plus 5.3% gives us 105.3%. And as a percent, that's 105.3 over 100. Which is, in fact, I'll move it over because I ran out of room. Isn't that cool on a digital canvas? So cool. This is 1.053. That's why you see this written as 1 plus r often in financial formulas, because you're adding the interest rate that you're increasing by. But it's easier to understand that this is just the thing I'm multiplying by every time my exponent happens. You could go lower with a 95% or 0.95. That would make it reduce its value by 5% each time you multiply. So anyway, we have our rate now, our multiplier, and we can raise it to the x power. This thing is a function that will tell us all the sets of x and y values that make this true. And I'll graph that for us so we can get a look at this function. All right, that's kind of the function. Notice we can't actually see anything, and we'll talk about why in a moment. One thing I want to note when you're using calculators, there's a character that looks like, here, I'll get a notepad out so you can see it. There's a character that looks like this on your keyboard or your cell phone. That's called a caret, and it's C-A-R-R-A-T, I think. I think that's how you spell that. And this is the exponent button. So if you're typing in a formula to a computer, you push the caret. Oops, that's not, I pushed the percent button. You push the caret, that's shift 6, and then you can use that as an exponent. In any case, we can't see this because the starting value, where it starts on the y-axis, is 100. So we need to zoom out quite a bit to be able to see that 100. Oops, not the whole thing. Try that again. There we go. We can kind of start to see it. And I'm going to zoom the x-axis in just a little bit more so that we have a better view of what's happening for the first 50 years of this thing. Oops, that was the y-axis. That would have been better if it was x. Y is going to get real big, so we'll just kind of start putting numbers in there until we get a good value. That looks pretty good. I like that. So anyway, let's put a table of values out for this thing. And you can kind of see at 0 years, we have $100. So the coordinate point, x is 0, y is 100. If we were to plug in 0 for x, you can see this thing is going to be 1, and we get $100 anywhere on that line, right? At the point 1, after 1 year, we have exactly 5.3% more interest added. So that's this point right here, not the negative one, this one right here. 1 year, we have now a total of 105.3. After 2 years, we have 110.88. That's what happens when you multiply this number by this percent, or this multiplier one more time. Anyway, you can kind of see the values. In the 3rd year, we'll have this much, and in the 4th, and the 5th, and 6th, and 7th years, we're kind of gaining value. By the time we get to 100 years, we're really gaining value kind of quickly at that point because we're getting interest on a much bigger number. So the amount of interest you get over time snowballs, and this is how you put interest to work for you to save money and to make sure that you can continue to keep the value of your money through economic pressures like deflation. So, okay. All that side content aside, to set you up for success with this first problem, now you have a lot of success here. What is the y-intercept of this? If we remember from before, our starting value in this format is going to be something times the multiplier to the x. So let's see how this fits. Something times the multiplier to the x. Something times the multiplier to the x. Oh, this is y equals 1 times 5 to the x. 1 times 5. So where's this starting? If we were to do this, it's going to start on the axis at 1 and go up from there. And it's going to multiply times 5 every time. So it actually is going to get big really, really fast. So kind of like it would be a very, very, very steep line if we were to try to draw this here. Very, very steep. And so our ordered pair, just so we can see it graphically as well, we said 1 times 5 to the x. You notice that gets big really, really fast. And we ask the question, where does this cross the axis? Where is the starting value? At 1, 0, 1. X is 0, y is 1. Woo! 9 minutes in, and we got the first one done, but now you have context for the rest of this stuff to be pretty easy. Okay, so we need to write this only as a fraction. Do not use equal signs. 8 to the first power means 8, and that's it. Negative 8 squared means we're going to take negative 8 and multiply it twice by itself. That negative inside the parentheses means that the negative 8 quantity gets squared. So a negative multiplied by a negative is a positive. But this thing, negative on the outside, means we're going to square the 8 first. Order of operations says we do parentheses and then exponents first. This negative right here is actually multiplication. It's a fancy way of writing negative 1 times 8 squared, if you want to look at it that way. Either way, we do the exponent first and get 64, then apply the negative, and we're good. So I'll write that out as negative 8. Negative quantity 8 times 8 is negative 64. There we go. Anything to the 0 is 1, period, end of story. except in the case where it's not, but that doesn't apply in this class. Everything to the 0 is 1. It's a good enough rule. This one's fun. It's 1 over 8 to the squared. 1 over 8 to the squared. This is really 8 to the negative 2, where the negative means that instead of multiplying by 64, we're dividing by 64. 1 over 64. If we multiply times 1 over 64, that's the same as dividing by 64. Or 1 over 8 times 8, I should write. Right? There we go. And then this guy here, 8 over 0, not possible, not a number. Your calculator may say error or it may say nan. There's some ways you can describe this. Not possible. We can't divide by 0. 0 divided by 8, though, does in fact equal 0. Because we're asking how many times does 8 go into 0. Okay, let's keep moving. I'll change of color here. Now we're looking at a function. Before I use the format y equals ab to the x, this is exactly the same thing, except a little more precise. We've said that a function, it's called f, that takes x as an input is ab to the x. It does functionally, pun intended, the same thing. This y and this f of x are the same quantity, but this is more specific because it allows us to give the function a name and specify which variable is the input. X is the input. So function notation is pretty helpful in math when you're trying to communicate precisely and there's multiple variables involved. So again, we still have the same format, and I'm going to very quickly just kind of write this. F of 1, we're saying x, find me the value of this function, find me the value of function f when you plug in 1 for x. That's what that says right here. So let's do that. That is f of 1 equals 5 times 3 to the 1, which is 15. There we go. F of 2 is 5 times 3 to the squared, 3 to the squared, which is 45. Remember, we're doing the exponent first, so this is 5 times 9, yeah? 5 times 3 to the third. 3 to the third is 27, so 27 times 5 is 110. If you want to know how I did that, I took 4 quarters. 5 times, oh, I got it wrong too. 5 times 27. 5 times 20 is 10. I was thinking 4 quarters is 100, but it's not. 5 quarters is 125, and then you got 2 more 5s, so it's 135. That's how I did that in my head when I actually did it right. That's why you check your math. And f of 0, remember what happens when you raise something to the power of 0, you get a 1. So this will just give us the value that we already knew for the start, 5. This thing starts at 5, 0, 5. All right, so here's another exponential. Just so that we remember, one more time, in this function, this is f of x equals 1 times 2 to the x. So the starting value is 1. And we know right away, without doing any math, that this 0 is going to be a value of 1 because that's where it starts on the y-axis. That's right here on the y-axis, not the x-axis. Yeah. And let's do some math so that we can kind of calculate this. I'm going to move this out of the way so we have a little more room. For negative 2. How about I zoom way the heck in and then we'll have as much room as I want. Okay, this is 2 to the negative 2. I need a thinner pen, but we can do that. No worries. 2 to the negative 2 is, this negative, again, is not the additive inverse, where we're saying it's the opposite of 6 is negative 6. This negative is a multiplication inverse because an exponent is repeated multiplication. So the opposite of multiplication is division. And say divide by 2 is the same thing as times 1/2. Right? So we're going to restate our thing that would have been times 4, or 4, into a division, just like this, as 1 over 4, or 1 over 2 times 2. That negative means multiplicative inverse. Okay, I had talked enough on that. Let's do it faster now. 2 to the negative 1 is just 1 over 2. Again, it's negative here means flip it over. It is now division or a fraction instead of being on top. We already know this is 1, but 2 to the 0 is 1. 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. And then we can kind of fill in this table if you know how to double your 2's repeatedly. Programmers actually know how to do this pretty well because in the good old days, this was a consideration of how many bytes you could fit into 2 to the 7. So a lot of old video games, the highest value you could get was 255, or sometimes even 127 was the highest value. Nerd out right there, because that is 2 to the 7th and 2 to the 8th. And that's how much information you could store in a byte. Okay, let's go to the other side. Like Adele, hello from the other side. Draw this graph using the points here. So I'm going to kind of steal this thing, and we'll bring it up so it's easier to see. Wow, that is too big. Please get smaller. There we go. And frankly, I mean, at -2, this is 1/4. So let's start graphing things. -2 is 1/4. -1 is 1/2. So -1, 1/2. I think you see the pattern here. At 1, we're going to do, I already put the 0. At 1, we're going to do 2. At 2, we're going to do 4. At 3, we're going to do 8. At 4, we're going to do 16. And 32 at 5. And then we're going to try to draw a smooth curve. This is going to be tough. That's pretty darn close. I think I did okay. So now we've drawn a smooth curve. It gets big really fast. What is the y-intercept? We've already talked about this. It's that one up here in this reddish burgundy-like color, which is 0, 1. We see that right here. When x is 0, and when x is 0, y is 1. Okay. Now, here's a definition of log. We did talk about this in class. If you didn't see it, there's actually some notes in this same notebook called Tuesday, October 28th notes. And this gives a little bit of a primer on some of the logarithm definitions and how that relates to interest and why we even care about logarithms. Turns out they're actually really dang useful in some certain mathematical situations. All right. I'm going to do this thing, but as a talk that I think will make a little bit more sense. And let me write it this way. I'll bring this over. They're saying that if x equals b to the y, then y equals log b of x. Let's use some vocabulary to help us remember. This is a base. Why? Because the base is raised to an exponent. So the base is the thing kind of holding the exponent up. That's your base. Which is really nice because this thing is also your base. That's why we put b right there. That's log base b. Log base b. And this is your base over here. Pretty cool. Okay, so log base b of x is how you'd pronounce this, is literally equal log base b of x. Maybe I'll do it in colors so you can kind of see the transition. Log, let's do purple base b of green x equals pink y. Yeah, that's going to be fun. All right. And now we're going to rewrite the same exact equation, except in exponential form. It's literally the same. Let's just substitute where the letters go. That b is purple. So you see the b, base b is on the bottom. The y is green. Oh, nope, y is not green. X is green. There we go. And y is pink. There we go. So just to make it really clear, log base b, the bases are kind of in the same spot. And actually, I'm going to move this over so they line up a little better. There we go. The x's connect. The y's connect, crossing. And the b's go straight down to the base. Boop, boo. It's like the Three Musketeers, 3 cool swords made for logarithms. Anyway, this is really cool because remember, this exponential form of an function is very much the same thing as this. But sometimes we want to be able to figure out what the exponent is when the exponent's a variable and we need to solve for the number of periods or the x that's in our exponent. Then we can use this nice nifty tool to make it so that log base b of a number x is just a number. It could be 6. We don't know. We'll practice that in a moment, but I wanted you to get the gist of what this definition is. So I'm actually going to move that thing over here for why we do this, so that you have that in your mind to kind of see how that works. And I'll move this up out of the way so it's not distracting. Here we go. Log base 2 of 8. Log base 2 of 8 is the same thing as, let's see if we can use the same colors. Green, and then equals y, like that. So we're going to use our same colors here. That's 2 to the y, that's the pink one, which is, yeah, this isn't helpful at all. 2 to the something equals 8. Huh, what power would I have to raise 2 to get 8? Well, 2 times 2 times 2 equals 8, so 2 to the third is 8. There we go, it is helpful. Why? Because 2 to the third is 8. 2 to the third is 8. Cool. Let's do some more. And maybe we can go a little bit faster here. 5 to the what is 25? Well, 5 squared is 25. I'm going to write it out in colors. Boom, bam, 5 squared is 25. All right, I think we kind of get the picture here. This is 10 to the what is 1,000. This one's 4 to the what is 64. And if you don't know, 4 times 4 is 16 times 4 is 64. That might be helpful. This one is 2 to the what is 32. We've already answered that question on the previous page right here. 2 to the 5th is 32. Times 2 times 2 times 2 times 2 equals 32. So, and then this one is a little bit more fun. What do we 10 to the what power is 1 over 100? I'm going to write that one out. Okay, I also wrote out the other ones. So for this one, we're trying to find an exponent that gives us 10 times something, or rather 10 to the what power will give us 1 over 100. If we want our multiplier to become a division or a divisor in this case, we're going to use a negative exponent. So 10 to the negative 1 would be 1 over 10. 10 to the negative 2 would be 1 over 100. So this is 10 to the negative 2 to give us 1 over 100. And just for the record, this negative, one more time, does not mean the opposite of positive 2. This is a multiplicative negative, which is why it causes us to flip over our fraction. Instead of being 100 over 1, this is now 1 over 100. They kind of flipped. Imagine this as a fraction that just flipped places like that. That's kind of trippy, actually. All right, let's go to the next place. This video is getting long in the tooth. So once again, we're trying to get from 2 to the what equals 1/8. And the answer is 2 to the negative third equals 1/8, because it's 1 over 2 times 2 times 2. So there's our result again. 5 to the what equals 1 over 5. 5 to the negative 1 is 1 over 5. 8 to the what equals 1. We always know if this says 1, the result is always going to be the same thing, because this is 8 to the what equals 1, which implies 8 to the 0 equals 1. 9 to the what equals 81. 9 squared equals 81. There we go. So we can see that kind of moving around these logarithm rules like this is really helpful, and as you start to practice more, it becomes, okay, I can maybe even do some of these in my head. You can do logs in your head. That's pretty cool, right? This is also a nice little note. When we write a logarithm without a base, it's usually base 10. Unless you're doing fancy college math, sometimes they assume that that is log base e. And also, there's another kind of log base e. We call it the natural log. So it can be a little bit confusing. For the sake of this course, log without a number is log base 10. Log, when it's ln, natural log, I don't know why it's backwards. Log natural. Euler was French. Yeah, that makes sense. Okay. So natural logarithm, base of e. E is just a number. It's a constant. It's like pi is a constant. It's this number. E has some really cool properties. In mathematics, if you try to find the rate of change of an exponential function e to the x, the value is always e. So at any given point, it's changing at a rate of e. That's super cool. It does some really nifty things mathematically. But you're not taking calculus, so that's probably less interesting to you. Let's evaluate this without a calculator. We're saying log base 10 of 10. So what we're really saying is 10 to the what? I'll write this down. 10 to the what equals 10. Once again, we're kind of like making that transition where the y's cross, the bases drop straight down, and I wrote them backwards so it actually doesn't work like that. So I'm not going to draw the lines. Either way, 10 to the 1 is 10. So we're looking for 1. Natural log of e. This is log base e of what equals e to the 1. So our result is just 1. 1. 10 to the what equals 1. We've already answered this question. For any logarithm, if the result is 1, then this is going to be 10 to the 0 equals 1. Natural log is log base e, but again, e to the what equals 1. E to the 0 equals 1. 10 to the what equals 100. 10 squared equals 100. Just so we're clear on which one's the answer there. There we go. And again, more of these. I'm just going to blast through this super fast. 7 squared is 49. Ooh, fancy. This is 1/10. So we're going to use negatives in our exponent to get that. This is 10 to the negative 1. So the result is negative 1 is the number we're looking for. 2 to the what equals 32. We've answered that multiple times tonight. 2 to the 5th equals 32. 3 to the what equals 3. 3 to the 1 equals 3. So 3 is the value we're looking for. 9 to the what equals 1. We've answered this repeatedly when you see a 1 in here. This is really 9 to the 0 equals 1. And 0 is our result that we're looking for. E to the what equals 1. Same thing. This is e to the 0 equals 1. 5 to the what equals 5 squared. That's kind of a fun question. So I'm actually going to write that down with the right colors. This is a really popular sort of question on SATs over the years because it requires that you really understand what logarithms do. In this case, what number do you have to put here to make these equal? And the result is 2. 2 is the number you have to put there to make those equal. So that's kind of a sneaky one. And then 4 to the what is 16. 4 squared is 16. And I think that is it, ladies and gentlemen. Congratulations, you can now do logs by hand. It's strange that I did them out of order, though. I'm not very happy about that. So let's go back up and do these in order. Here we go. Logarithms on your calculators may be done differently depending on what calculator you have. I'm actually going to move some of this over so that it's, oh man, maybe I should put the calculator on the other side. There we go. There we go. Log base 10 of 50. A lot of calculators have a log button. This one, you see that it's red right here. I don't know why you can't see the mouse finder, but anyway, you'd hit the control button to use the red buttons, and then you just kind of type it in. And another way you can do this is using commas on this calculator. So log of 50 comma base 10 will give the result we're looking for. You notice that when I typed that in, it did log base 10 of 50. And then some calculators, when you do your logarithm, you will actually have spaces that you have to write in where it says the base and the number you're taking the logarithm of. So log base 10 of 50 is approximately that. I'm just going to copy it out of the calculator because it's fast. And then we'll do 105. Oops. Come here, you. There we go. No sweat. And you don't need to see me do the rest of these. Maybe you do. Natural log. On most calculators, there is also a natural log button. It's just ln, scientific or graphing calculator like this one. And you get whatever you get. Wasn't that fun? All right, so logarithms are irrational numbers. That means essentially that, how do I even explain irrational numbers? A rational number is a number that can be expressed as a ratio of two whole numbers. So 2 over 7 is a rational number. If you type that in your calculator, you're going to eventually get a set of repeating decimals. This calculator, unless I tell it to solve approximately, you're going to get 2, 8, 5, 7, 1, 4. and then it's going to repeat again, 2, 8, 5, 7, 1, 4, and that decimal repeats. So all fractions of whole numbers repeat in their decimals. That's what makes them a rational number. Even 1/3 repeats. You can kind of see that the 3 just repeats forever. But then there's numbers like pi. Is there a pi button on here? Yeah, here, let's just, let's just put e in there. That's an irrational number, which we don't do with control there. Will you stop that, you silly calculator? We'll just put e in there. That's the value of e. This doesn't repeat anywhere. There's no repetition in these decimals, and that goes on forever. That's called irrational. It cannot be expressed precisely as a ratio or fraction of two whole numbers. Okay, so there's rational numbers. Irrational, like pi or square root of 2 or other numbers like that, kind of fit between and can't be expressed as a fraction of whole numbers. Wow, consecutive integers. So this is actually a fun problem. I suggest that you try this without me showing you how to do it if you're watching. I know this is kind of a long video at this point, but this is worth trying to do. Really what we're saying here is 10 to the what equals 85. And we know that 10 squared is 100, and we know that 10 to the 1 is 10. So between 1 and 2 is 85, right? That's pretty cool. When we say integers, just so we're clear, those are whole numbers. It could be positive or negative whole numbers. Okay, so this one says 3 to the 85. So 3 to the what equals 85? Well, we don't really know, but we do know that 3 to the third is 81, because 3 times 3 is 9, times 3 is 27. Oh, I totally got that wrong. 3 to the fourth is 81. There we go. And 3 to the fifth is bigger than that. So this is somewhere between 4 and 5. All right, I'm going to leave this here. Cool, so now we have 4 to the what equals 85. Well, let's see. 4 squared is 16. 4 to the third is 64. 4 to the fourth is a whole lot bigger. I don't even care. It's 256, I think. Yep. So this is between 4 to the third and 4 to the fourth. Pretty cool. I think you get the picture now. Oh, gosh. 60 to the what? 60 to the 1 is 60. And 60 squared is much, much bigger. That's 3,600. So this is between 1 and 2. And for our last one, 7 to the what? So 7 to the squared is 49. And 7 to the third is bigger. Whatever 49 times 7 is, it's slightly smaller than 350. So there we go. Pretty cool. Okay, scientific notation, just so we can understand. 4 times 10 to the negative 9th is the same thing as saying 4, but let's move the decimal to the left 9 times. So we're going to have 8 zeros to the left of this number when we finally get done with that. So it's really the log of, let's see if I can write this small enough, log base 10 of that number right there. It's a very small number. Or if you want to be sneaky and use the exponents here, we can actually write this as, instead of 4 times 10 to the negative 9, we can write this as a fraction. But for putting it in the calculator, we're just going to use this notation to make it easy since we're using a scientific calculator. I just wanted to make sure we understand what the times 10 to the negative 9 actually means. It means divide by 10 9 times. Take 4 and divide it by 10 9 times. And we get that value. Just so we can really see what that looks like, this is 4 divided by 10, and so on, and so on. Did I screw it up? I sure as heck did. Ugh. Divided by 10. And you can kind of see what's happening. Every time we divide by 10, that e goes up another number. So that's 4e negative 9, which is the same as 4 times 10 to the negative 9. We've divided by 10 9 times. Now we need to take that thing, that value, and we're going to take the logarithm of that. So we can push our log button. It's log base. That's not a log. There we go. Log base 10. I think if we leave it blank, it'll just work. Of that. Go. Yeah, that's correct. Cool. Let's put it in there. And kind of the same thing for this next one. We're really just going to type it in. Log base 10 of 7 times 10 to the fourth. Let's actually type it in this time. 7 times 10 caret to the negative. You have to use this negative down here, not the negative that is the minus operation. Although I think this calculator figures it out, some of them don't. And then that should be good. And there we go. Looking good, looking groovy. Rewrite this as an exponential equation. We did that up above already, so I'll just go grab the one that I already did and bring it back down here. And since it's too tall, I'll make it smaller. Oof, that's kind of cramped. There you go. And whew, 35 minutes in. That's our longest video yet, and we are done. Hopefully this makes logs make more sense. Have a great life.